orthogonality is an important issue on circles, and some important things related to orthogonality is what I am going to tell you, which could act as ready reckoners for problem solving of a certain variety. Now, the statement that I make here is that if a circle cuts two circles orthogonally, if there are two fixed circles, circles 1 and circle 2, circle 1 and circle 2, and if there is a circle cutting these two circles orthogonally, then its center must lie on the radical axis of the two circles. So you know these are two fixed circles with centers C1 and C2. Refer to these circles as 1 and 2. And there is this circle, you know, the one that you see in blue line, the one that you see in blue ink. It has its center at C somewhere, and it is cutting circles 1 and 2 orthogonally. It's cutting circles 1 and 2 orthogonally. Now, if C is the center, L is the radius of the circle, and R1 is the radius of this circle. So L will be perpendicular to R1 because this circle with center C is cutting this circle orthogonally. So L is also the radius of this circle, which is cutting this circle orthogonally, right? What we want to show is, so it's you know, if L is the radius of this circle cutting these two circles orthogonally, R2 is the radius of this circle, then what we want to show is this circle, which is cutting these two fixed circles orthogonally, has its center that lies on the radical axis of these two circles. That's what we want to establish. Okay. Refer to these. So I repeat, what is it that we are trying to achieve here? Given two fixed circles and a third circle which is cutting these two circles orthogonally, we want to show that the center of this circle will lie on the radical axis of these two circles. That's what we want to show. So first of all, so let me call this third circle which is cutting these two circles orthogonally as circle 3, right? 1 and 2 are fixed circles, and the third circle can have its center anywhere on the radical axis. So third one could be a variable circle. One way or the other, let me prove these results. Let's prove these results. So let me refer to circle 1. Let me refer to circle 1 as x square plus y square plus 2g1x plus 2f1y plus c1 equal to 0. Let me refer to circle 2 as x square plus y square plus 2g2x plus 2f2y plus c2 equal to 0. These are the two fixed circles, circle 1 and circle 2, right? And there is this third circle. There is this third circle which I refer to as, say, x square plus y square plus 2gx plus 2fy plus c equal to 0 is this third circle. What we want to show is the center of the circle, which is minus g comma minus f, the center of the circle, this, right, lies on the radical axis of 1 and 2. Lies on the radical axis of 1 and 2. That's what we want to show. Given that the third circle intersects 1 and 2 orthogonally. So first of all, let me write down the condition for orthogonality of 3 with 1 and orthogonality of 3 with 2. This circle 3 is cutting 1 orthogonally. This circle 3 is cutting 2 orthogonally. So orthogonality of 1 and 3. Condition for orthogonality is like a 2g1, 2g1g, 2g1g plus 2f1f is c1 plus c. Let me call that as equation 1, right? And orthogonality of 2 and 3 will give me like a 2g2g plus 2f2f equal to c2 plus c. That's orthogonality of 2 and 3. Now, given this we want to show that the center minus g minus f of this circle, which is cutting 1 and 2 orthogonally, will lie on the radical axis of 1 and 2. Now, what about the radical axis of 1 and 2? Look, the radical axis of 1 and 2, radical axis of 1 and 2 of 1 and 2 is what? Radical axis of 1 and 2 is this equation minus this equation equal to 0 will give me the equation of the radical axis. What's the property of the radical axis? The length of the tangents from any point on the radical axis would be the same for the two circles. That means if I take any point on the radical axis, its distance, its length of the tangent to this circle will be equal to the length of the tangent to the other circle, right? So I'm not getting into that because we've had a sumptuous discussion on radical axis already. So then, radical axis of 1 and 2 is what? This minus this. That means twice g1 minus g2 into x plus twice f1 minus f2 into y plus c1 minus c2 equal to 0, right? Now we want to show that the center of this minus g comma minus f, the center of this third circle cutting 1 and 2 orthogonally will lie on the radical axis. That means minus g comma minus f will satisfy this equation. That's what we want to show. So let me plug in x equal to minus g and y equal to minus f in the left hand side. What do I get? I get like a minus twice. I take minus twice common from these two, replacing g by x by minus g, f by minus y. I get like a g1 minus g2 into g plus f1 minus f2 into f plus c1 minus c2. This is what I get, right? Now what happens from this point onwards? realize that I could have rewritten this as see g1g f1f. I combine twice g1g plus f1f, twice g1g plus f1f. So I take this 2 inside, and that will help me make the algebra a little better. So twice, and then I make this also twice, so that I can have 2 g1g twice g1g plus twice f1f, right? And then minus twice g2g plus twice f2f is what I get, right? And then there is a plus c1 minus c2 remaining outside. Now that's making life really easy for us, because realize twice g1g plus twice f1f, twice g1g plus twice f1f is actually c1 plus c. So this is like a minus of c1 plus c, and minus twice g2g plus twice f2f, twice g2g plus twice f2f is like a c2 plus c. So minus c2 plus c and plus c1 minus c2. This is what happens. Hey, this c and this c will get cancelled, and then minus c1 will get cancelled with plus c1, and then plus c minus plus c2 will get cancelled with minus c2. So this is turning out to be 0. That means the point minus g comma minus f, which is the center of the third circle, lies on the radical axis of 1 and 2. Now that's really important to know. So keep this in mind. If I have two fixed circles, and there is a third circle cutting circles 1 and 2 orthogonally, then the center of this third circle, the blue ink, the center of the circle, the blue ink, will lie on the radical axis of 1 and 2, right? Now, an important corollary out of this. So one thing, the center of all circles cutting 1 and 2 orthogonally will have a locus which lies on the radical axis. If you select any point on the radical axis of 1 and 2 and draw a circle, whose radius, the radius of the circle, by the way, should be equal to the length of the tangent drawn from that point on the radical axis to either of the two circles, right, which will be equal in length. The radius of this circle will be L. L will be the radius of circle 3, which is the length of the tangent drawn from a point on the radical axis to any one of the two circles, right? So with C as the center and with radius equal to the length of the tangents drawn to the two circles from any point on the radical axis, if you draw a circle, then that circle will cut the two mother circles orthogonally, right? Now, very clearly I could have selected different C's, different points on the radical axis. I would have got this circle, the blue circle, of varying radius L. L is the radius of this circle. Now the point is, what point should I select as the center? What should be the center of the third circle, so that the radius of the third circle is the smallest? That means I want the smallest third circle cutting these two circles orthogonally. Now let me tell you, the center of this circle must coincide with O. The center of the circle must coincide with O. If O becomes the center, you know, this is this point on the radical axis, the point of intersection of the line joining the centers of the two circle and the radical axis is O. If this is the center, I draw a circle, right, whose radius is equal to the length of the tangent drawn from O to either of the two circles, then that circle will have the smallest radius, Y. That means of all the orthogonal circles whose center lies on the radical axis, the one whose center is this O is the one of smallest radius. That will be the smallest circle. How does one prove that? Let me get into that. That's very ordinary geometry. Let's see how that happens. So, can I wipe this off? Yes. Let's see how that works. Look, this is one circle, this is another circle, this is the radical axis of the two circles, right? This circle is has center C1, this circle has center C2, right? And this is the radical axis of the two circles. And I select a point say C on the radical axis, and I draw a circle whose radius is equal to the length of the tangents drawn to the two circles. Then the smallest value of L will happen. L will be smallest when C coincides with O. Let's see how that works. That's fairly simple. That means if this length is Y, when Y turns out to be 0, when this Y turns out to be 0, then this third circle will be the smallest possible third circle. Now, this is R1 as you can see, and since this third circle and this circle cut each other orthogonally, this is a tangent. L will be perpendicular to R1. L is the radius of this third circle, right, which is also the length of the tangent drawn from C onto either of the two circles. Now, obviously, you know, this point on the radical axis is a fixed point. Let me call it L0. That's a fixed number. R1 is a fixed number. L could be varied. L is the radius of the third circle, which could be varied based on the choice of C. Now, I want to minimize Y. I want to minimize L. L could be varied. L will depend on where Y is, how much Y is. I want to show that L will be minimum when Y is numerically the smallest and is equal to 0. Easy to see. Hey, what is C1C whole squared? C1C whole squared is L0 squared plus Y squared. That's C1C whole squared, right? And see from this Y squared plus L0 squared. But C1C whole squared is also L squared plus R1 squared. R squared. R1 is a fixed number, the radius of this fixed circle. L0, that's a fixed point because these two are fixed circles. So O is a fixed point, so L0 is a fixed number. So very clearly, L squared, which is L0 squared plus Y squared minus R1 squared would be minimum. When Y is 0. y0 means, so the center of the third circle is this point on the radical axis, If you draw a circle, that's a smaller circle you could have drawn. Yes or no? So of all the circles with points on the radical axis as their centers, the smallest would be the one whose center is this point O. That's a circle with the smallest radius. That means when y turns out to be 0, L0 turns out to be the least it could be, and the L minimum is like when y is 0 is L0 squared minus R1 squared. So L minimum will be root L0 squared minus R1 squared. Right? So this extremely important result. So what are the two things that you've got to hang off by the time this session is over? In this session you've learned, given two fixed circles, and there is a third circle which is cutting these two fixed circles orthogonally, then the center of this third circle can be anywhere on the radical axis of the first two circles, and the radius of the circle would be the length of the tangent drawn from its center onto either of the two circles, which will be equal because this is a point on the radical axis. So L will be the radius of the third circle, which could be varied based on choice of C, right? And the minimum value of L happens when C coincides with O. That means the center of the third circle lies on the line joining the centers of the two fixed circles, which is also the point of its intersection with their radical axis. Yes or no? Thank you so much. Bye-bye. One very basic fact, that if there is a circle cutting two given fixed circles orthogonally, then the center of the circle must lie on the radical axis of the two circles. Now here we have a modification of that previous result. Instead of two circles, I'll take three fixed circles, 1, 2 and 3. These are three fixed circles with their centers C1, C2 and C3. What I want to show is that if there is a third circle, and of course we'll assume that C1, C2, C3, their centers are non-collinear points. Now what we want to establish is that if there is a third circle cutting C1, C2 and C3 orthogonally, right, each of C1, C2, C3 orthogonally, then the center of that third circle must be the radical center of these three circles. I hope you haven't forgotten your radical center concept. If yes, go back to my radical center class, radical axis class, and get yourself on with things. Now, look at this. So, given three fixed circles, I'm trying to locate a third circle. There'll be only one third circle this time. If there were two fixed circles and a circle cutting two fixed circles orthogonally, there could be multitude of circles. But given three fixed circles, there'll be one and only one circle cutting the three circles orthogonally. How? Look, this is radical axis 1, radical axis of circle 1 and 2, right? So the center of the circle cutting 1 and 2 orthogonally must lie on the radical axis of 1, right? Similarly, refer to circles 2 and 3. Now the circle that I'm talking of also cuts 2 and 3 orthogonally, right? That means the center of that circle must lie on the radical axis of 2 and 3, which is along this. And it also cuts 1 and 3 orthogonally. That means the center of that circle cutting 1 and 3 orthogonally must lie on the radical axis of 1 and 3. That means the center of the circle cutting each of the three circles orthogonally must lie on each of the three radical axes. And we know the three radical axes taken in pairs are concurrent lines, and they intersect at O, which is called the radical center. That means the center of the required circle. This will be the center of the required circle. This is the center of the required circle, right? Which is, you can find the equation of any two radical axes and find their point of intersection O, and that will be the center of the required circle. And what about the radius? Obviously, now that's easy to see. A circle cutting 1 and 2 orthogonally, having center at O, the radius of such a circle, right? It's cutting 1 and 2 orthogonally, for example. The radius of such a circle whose center is O And cutting 1 and 2 orthogonally, as we have discussed in the previous section, will be OP, the length of the tangent. This is R1. OP, the length of the tangent from the radical center to any one of the three circles. From O, the tangent drawn to 1, tangent drawn to 2, and tangent drawn to 3 would be all equal in length. Yes or no? So, evidently, the radius of that circle will be the length L. L, the length of the tangent drawn from O to any one of the three circles will be equal to the radius of the required circle. O is a fixed point. So the center of the required circle is a fixed point. And L, the length of the tangent from a fixed point to a fixed circle, will be constant, will be a fixed number L. So that circle has center O and radius L. So if O turns out to be h comma k, and L, the length of the tangent, turns out to be L, then the required circle is going to be x minus h whole squared plus y minus k whole squared equal to L squared, where hk is what? Intersection of the three radical axes taken in pairs, which is the radical center. What is L? L is the length of the tangent drawn from hk. Once you know hk, you can find the length L of the tangent, root S1 kind of a formula, to any one of the three circles, right? From the radical axis, the tangents drawn to each of the three circles will be L only. So here we have a third circle. What is its property? If it is cutting all the three fixed circles orthogonally, it must have its center as the radical center. It must have its radius as the length of the tangent from the radical center to any one of the three circles. If from O I draw a tangent to this, say OQ, that will also be L. If from O I draw a tangent to this, OR, that will also be L, and so on and so forth. So that will be my required circle, right? So this is an important result. But if their centers are collinear, if three circles are such that their centers are collinear points, then we don't talk of a radical circle. We don't talk of a circle orthogonal to the three circles. Then the straight line joining their centers, straight line joining the three centers, would be the orthogonal straight line, which is cutting the three circles orthogonally, right? We then don't talk of an orthogonal circle, we talk of an orthogonal straight line, cutting the three circles orthogonally. So this is important to understand. I repeat, the two results: one, given two fixed circles, a third circle which is cutting these two circles orthogonally will have its center lying on the radical axis of the two circles, and the locus of the center of this third circle would be any point on the radical axis. It would be a circle with varying center and therefore varying radius. The radius of that circle will be the length of the tangent drawn from any point on the radical axis to any of the two circles. As a consequence of this, we learnt another thing. What is that? If we have three fixed circles whose centers are non-collinear, then there exists a unique circle which is orthogonal to the three circles. The center of such a circle will be the radical center of the three circles. The center of such a circle orthogonal to the three circles will have the radical center as the center, and its radius would be the length of the tangent drawn from the radical center to any one of the three circles. Yes or no? Right? Keep these two results in mind. It'll help. Thank you so much. Bye-bye.